All right, ladies and gentlemen, welcome back to section 4.5. We're talking about differentials one more time. And so let's get going here. Below the picture here, we're going to start off by reviewing our differentials formulas from the last notes. So remember, the differential dy, which remember represents the approximate change in the y values, right? Dy is the derivative of your function times the change in x. Remember, delta x dx, those are going to be the same thing, okay? So the differential dy is the same as the differential df, right? So sometimes we write y is a function of x, right? Y equals f of x, right? The second way is just kind of keeping the variables the same, right? So df is the differential of the output, which would be f of x, right? So we get the same formula there, okay? But we're going to take a look at differentials in the context of some scenarios, some word problems, and in those, we're going to use differentials to calculate a couple of things, okay? The first thing we're going to calculate is something called absolute change, okay? Absolute change is just going to be the differential of the output itself, okay? This can also be called maximum possible change. So what is the most change that could possibly exist when something happens, right? Now, another thing you're going to notice in all the stuff that we're going to write down here is you'll see the word error, okay? Because in some of these contexts, what we're talking about is something is changing, but that could result in an error, right? Remember, the differential is an approximation of the actual change in the output, right? And so since we are approximating, that could be considered an error, okay? So the words change and error are going to be used interchangeably here, okay? So anytime you see the word change, you may also see the word error, and you are asked to find the same thing. So what's the maximum possible error in calculating something, right? That would mean just finding the differential of the output, okay? Relative change is another thing we're going to calculate, or relative error, and that is going to be the ratio of the differential of the output compared to the original output, okay? So df over f of a, where a represents like the initial value of something. So we'll see this in the context, it'll make a lot more sense, okay? And the last thing we're going to calculate is percent change or percent error. Okay, and now the nice thing with percent change or percent error is it is just going to be your relative change, so the differential over the original function times 100. It's turning that decimal into a percent. Okay, so these are the formulas that we're going to be using, and it's going to be up to you when we look through these questions to figure out what formula corresponds to what, okay? So let's see this in an example, and this will start clicking here, okay? So let's look at example 8. The radius of a circle increases from 10 meters to 10.1 meters. Now, this tells us a lot of things, okay? First of all, it tells me what the starting radius is. The starting radius is 10 meters, right? And what does it change to? It goes from 10, changes to 10.1. That tells me that the change in the radius, dr or delta r, right? Because those are going to be the same. That is going to be 0.1. Okay. So that tells me two crucial things, okay? Now, it says use dA, so this is the differential of A. Now, I don't know at this point what A means, but you can kind of think back to geometry. What does A usually refer to? Use dA to estimate the increase in the circle's area A, okay? And then it says estimate as a percentage of the circle's original area. So we'll get to all of that, okay? Now, the main thing we want to focus on here is we want to find the area of a circle, right? and the radius, okay? And so let's think back to geometry, right? What's the area of a circle formula, right? We all know this, it is pi r squared. But the way I'm going to write it is that I am going to treat this as a function. What is the area of a circle as a function of that circle's radius? What is a of r? A of r is going to be pi r squared. So you are going to be responsible for some geometry formulas in this section, okay? Okay, so area of a circle as a function of its radius, right? A of r is pi r squared. Now, what we're going to do is we're going to take the derivative of this with respect to the radius, okay? Not x, right? Not d dx, which I know is what we're used to writing, right? But this is a function of r, and that's specifically why I wrote a of r here instead of just writing a equals pi r squared, right? The input variable is r, everything is with respect to r, okay? Okay, I'm going to start with the right-hand side here, because that's going to be the easier side. Pi r squared, right? Again, derivative with respect to r. This is just going to be the power rule. And so the 2 comes down. I get 2 pi, and then r goes to the first power, so which I get just 2 pi r. Okay, and now something interesting I want you to notice. What is the derivative of the area of a circle formula? 2 pi r, which is the circumference. Just a little fun fact. Okay, and now on the other side, right, what is the derivative of a of r? Well, think of a as like the name of a function, right? Well, what would we say is the derivative of f of x, right? We would say f prime. Now, we could say a prime here, right? But we want to think of this in terms of differentials, right? And so this is going to be the differential of a, the area, with respect to the differential dr. So dA dr, okay, this is another way of writing a prime of r. Just like how the derivative of f of x is f prime of x, right? We can write that as df over dx. I'm using the same idea here. This is dA over dr. And now I'm going to go ahead and multiply the dr over to the other side. And so I get 2 pi r times dr. And I will put a little dot there just because RDR looks a little weird. Okay. Okay, so now I have the formula for the differential for the area. And now we're going to do what we did last section, right? So I know my initial R value. R is going to be 10, and then it is going to increase by 0.1 meters. And so I can plug those in, and I can calculate. And so I can get 2 pi times my R value times my dr value. 2 pi times 10 times 0.1. So 10 times 0.1, well, 0.1 is 1/10, right? So 10 times 1/10 is 1, right? I can ignore that. And so I get just 2 pi times 1, which is 2 pi. Okay. Now, one thing that makes this section different than the last section is almost every question we do here is going to involve some sort of units, right? Because I'm estimating a change in the area, right? So as this circle increases by 0.1 meters, that means the area of that circle is going to increase by approximately 2 pi meters squared, okay? So we have to pay attention to units, all right? And so this right here, we could call this a few things, right? We could call this the differential dA like we just did. We could call this the absolute change in the area, right? So a way of thinking about absolute change, like why it's worded like that, is this is saying like at most, right, what is the biggest possible change? What is the absolute biggest possible change the area could have? And that's going to be 2 pi meters squared, okay? Okay, and that's also why we call it, maximum possible change or maximum possible error, okay? Okay, now I'm going to find the relative change. So what the relative change is it is the ratio of the differential, which we just calculated for the area, right? We're going to compare that to the original, right? What was the area of this circle when we originally started? Well, that would be the area when the radius was 10, right? So pi times 10 squared, pi r squared, that's 100 pi, okay? And now I'm going to take the ratio of those two calculations, dA over the area when the radius was 10. So dA is 2 pi, and the area when the radius was 10 was 100 pi. And the pi's cancel out, and 2 divided by 100 is 0.02. And so this decimal here represents the relative change. Okay, and the last thing, and this is a little hint for the quiz and test this chapter, I'm never going to have you answer a question with the relative change, right? You're going to calculate relative change a lot. You're going to use it in calculations, but I'm always going to ask you for a percent, right? So we take that 0.02, multiply it by 100, and we get 2%, okay? So all of this is telling me that at most, right, when the radius goes from 10 to 10.1, at most, we're going to get a 2% change in the area of the circle here. Okay. So that's what we're actually calculating. All right, is again, all of this is approximations, right? Look back at the last note sheets. Differentials, we use those to approximate. Okay. Okay, let's take a look at another example. Very similar though. Okay. Example 9. Inflating a bicycle tire changes its radius from 12 inches to 13 inches. So again, I learned two important things here. One, the initial radius is 12 inches, and that the change in the radius is 1 inch. Estimate the absolute change, the relative change, and the percentage of its circumference, okay? So bike tire, right, we're going to treat it like a perfect circle, okay? Circumference formula for a circle, we just talked about it up above, right? It is 2 pi r. But this is the circumference specifically as a function of the radius of the circle. As you may recall from geometry, right, you have a circumference formula in terms of the diameter of the circle, right? If this question wanted us to do stuff with the diameter, right, we totally could, because you should remember that the diameter formula for the circumference is pi times the diameter, right? So the circumference as a function of d is pi d, right? But that's not what this question's asking for, right? So I'm going to put everything back in terms of r for my radius. Okay, so the circumference as a function of r is 2 pi r. Take the derivative with respect to my input, which is r, so d dr, okay? And so I'm going to get on the left-hand side the differential of the circumference over the differential of the radius, dc dr, equals, and on the right-hand side, 2 pi r. R is to the first power there, so when I take the derivative, right, the 1 comes down, so I just get 2 pi, but r goes to the 0 power, so it goes away. And so I get just 2 pi. Okay? And now I'm going to go ahead and multiply the dr over to the other side. And so we get dc equals 2 pi times dr. Okay, so there's my formula for the differential of the circumference. Now, one thing that's going to be true with all of these questions, because we're going to talk about lots of geometric formulas here, a lot of stuff from geometry is going to come flooding back to you, right? It doesn't matter what the context of the question is. If you're looking for the differential of the circumference, this is the formula. Now, I don't recommend that you try to memorize all these differential formulas. If you want to, you can. But I think it's in your best interest just to, go back to some geometry notes, remember these, right? And if you happen to remember some differentials because you practice with them and they look familiar, that's great. Okay. Okay. So we want to calculate absolute change, right? So what's the biggest that the circumference could change by, right? So that's going to be the differential of just the circumference. So DC is going to be 2 pi times dr. So the radius went 12 inches to 13 inches. So the change in the radius is 1, right? So 2 pi times 1 is going to be 2 pi. And for this, we need inches for the units of the circumference. So at most, the circumference is going to go up by 2 pi. Okay, what's the relative change? So let's take the differential of the circumference and divide it by the original circumference. So the circumference when r was 12, not 13, 12, the starting value. Okay, so I can take my absolute change from up here, so 2 pi, divided by the circumference formula when the radius is 12, so 2 pi r, so 2 pi times a radius of 12, and now 2 pi's can cancel, and so I get 1 over 12, which I'm going to write as a decimal, which you may know, but if you don't, that's okay. It is 0.083 repeating. And the last thing, we can quickly turn that into a percent by multiplying by 100, and we get an 8.3 repeating percent change for the circumference. Okay, so at most, the circumference is going to go up by 8.3 repeating percent. Okay, all right. So let's keep going. Let's take a look at another scenario with another geometric formula that hopefully we remember. Let's look at example 10. Okay. Suppose the Earth were a perfect sphere. So we're going to assume it's pretty close, actually, but it's not quite. It's pretty close to being a perfect sphere, though. And we determined its radius to be 3,959 plus or minus 0.1 miles. Estimate the percentage error in the Earth's surface area calculation. So we want surface area of a sphere. We're going to come back to that. I want to go back to this approximation for the radius. Okay, so the way we interpret this is that the initial radius, we're going to say, is 3,959 miles, but the change could be plus or minus 0.1. It could be 0.1 mile bigger, it could be 0.1 mile smaller. We're not quite sure. Okay, so if you see a stat like that, right, so take the initial value and let that be, whatever your input variable is, and then whatever is plus or minus, that's going to represent your change. Okay, so I want surface area of a sphere in terms of its radius, right? And so this is a formula you may have learned in the past. If you take an orange peel, right, and take it off, you're going to discover that the peel of an orange will give you approximately 4 times the area of a circle, 4 pi r squared. Okay, that's a fun project to do while you're at home right now. Okay, so surface area as a function of the radius is 4 pi r squared. So we're going to take the derivative of this with respect to r. Okay, I've talked about this in another video. I like to write SA for surface area. If you want to write just A, that's fine. Okay, it's not going to matter. If you want to write just S, that's fine. I like writing SA. Okay, so I'm going to get the differential for my surface area over the differential for the radius. On the right-hand side, we do the power rule, and so we get 8 pi r. And now we multiply the differential for the radius over to the other side, and we get the differential for the surface area to be 8 pi r times dr. Okay, so here's my formula. All right, now again, you can memorize this if you want, but I want to see this work no matter what. Okay, so I want you to show me starting off with the correct geometric formula. You take the derivative with the correct, with respect to the correct input variable, not x every time, okay, right? And then you multiply the differential of the input over to the other side to get the differential of the output, which in this case is surface area. Okay, so I'm going to show you how to do this question in two different ways from this point, because there's a way that we've been doing it that we don't have to. I'll show you that in a little bit, but first let's get to the percentage error. Okay, so here's the other thing, by the way. We don't have to actually separately calculate the differential for the output or my absolute change, right? I can calculate this in the process of just calculating the percent change, which is all our question is asking us to do. Okay, so I want to know what is the differential of the surface area over the initial surface area when we have a radius of 3,959. And I like to do this, and then at the end we'll multiply it by 100 to turn it into a percent. Okay, so we're going to get 8 pi r dr for the numerator, so 8 pi. My radius is 3959, and I'm going to write plus or minus 0.1 here, okay? And the reason why I'm leaving the plus or minus in is because ultimately we don't care if our estimate is too big or too small from the actual value, right? We want to just determine what is the maximum possible change, whether that change is a positive change or a negative change, okay? And we're going to divide this by 4 pi times the radius 3959 squared. Okay, now you can pause the video and do this on your calculator if you want. Okay, so you can go ahead and pause it right now if you want to do that. But I'm just going to say the answer, which is plus or minus 0. And you got to be careful here. 1, 2, 3, 4 zeros, 505. Okay, and it keeps going. I think it's like 178 or something after that. All right, but this is actually the relative change, right? So by the way, just to think about what this is saying, if our estimation of the radius of the Earth is off by just 1/10 of a mile, 1/10 of a mile is not an insignificant amount, right? 528 feet, right? But in regards to the effect it would have on the surface area of the Earth, that's a very tiny number, right? And if we convert this into a decimal and round to 3 decimal places, right? Or I'm sorry, I said convert it to a decimal. I meant convert it to a percent and round it to 3 decimal places, we would get 0.005%. Okay? Now, when we do a percent, we drop the plus or minus, right? Because the percent is, again, not caring about whether or not this is a positive change or a negative change, right? But overall, a very minuscule amount is what we're saying, okay? Okay, so this is one way to calculate relative change and percent change, and that's the way we've done these last two questions, right? Is we set up the formula, we plug in all of our numbers, right? And then we simplify, okay? But I want to show you another way of doing this, all right? And so I want to pick it up from right here, the differential of the surface area over the surface area, but this time I'm not going to plug in the r of 3959. I'm going to leave it as a variable. So the differential of the surface area over the surface area for just some r. Okay, so now I'm going to plug in my differential formula, 8 pi r times dr over 4 pi times r squared. Okay, and before I plug in anything, what I'm going to do is I'm actually going to simplify this formula, because you're going to notice that a lot of things here can be simplified, right? So for example, what is 8 divided by 4? Well, 8 divided by 4 is 2, right? What is pi divided by pi? Well, those cancel out. We get 1. What is r divided by r squared? Well, that's just going to leave me with 1r in the denominator. And the dr cancels with nothing, right? And so I am left with just 2 dr over r. And so I'm going to get 2. Now I can plug everything in. My dr was plus or minus 0.1 over the initial radius of 3,959. And if you do this fraction in your calculator, right, you don't have to plug in the plus or minus. You'll see it. You can write it at the end. You're going to get same thing. You're going to get plus or minus 0.40505. And that converts to the same percent, 0.005%. Okay? So it doesn't matter which of these two methods you choose to do, right? Once you get the differential, you can immediately plug in the r value, right? Go to the calculator and simplify everything. Or you can simplify the formulas first, right? And then plug in your numbers, and now you have a smaller calculation to do. Okay, I like this second way because we're actually going to be using that in the next example. So I think this is a good skill to have. Okay, and let's take a look at that next example. All right, example 7 starts off a little bit differently. It says, about how accurately should we measure the radius of a sphere to calculate the surface area within 1% of its true value? Okay, how accurately should we measure the radius of a sphere? Now, I'm going to go ahead and rephrase this for you. If you see a question that's phrased like this, what it's really asking you to find is what should the percentage error of the radius be? Or more specifically, the percentage error of the radius has to be less than or equal to what? Okay, so in other words, what is like the most we can be off by in measuring the radius as a percent, right? What is the most we can be off by so that the surface area is still within 1% of its true value? Okay, that's the goal. All right, so let's talk about this. Okay, now one thing that's going to make this question nice and easy is we're talking about surface area of a sphere again, right? So I'm not going to actually write out any work here. I'm going to go back up here because, hey, we already figured out the calculation for the differential of the surface area, right? And it doesn't matter what sphere you're talking about, right? It's still going to be the same exact calculation. So I'm going to use that to my advantage. Okay, so the differential of the surface area is still 8 pi r dr. Okay, now what this question is saying is I want the surface area to have a percent error no greater than 1% of its true value. That means that the differential of the surface area is the surface area with some other radius, right? So the differential of the surface area over the initial surface area has to be less than or equal to 1%. Remember, I'm writing this now in terms of relative change, so I have to divide by 100. So this is going to be 0.01 that it has to be less than or equal to. Okay, and so now what I'm going to do is I'm going to plug in those two formulas. So 8 pi r dr divided by the surface area, which is 4 pi times r squared. And again, this has to be less than or equal to 0.01. Again, the 0.01 is because we want the surface area to be within 1% of its true value. Okay? And so now I'm going to do just what I did at the end of the last question. I'm going to simplify this fraction a little bit. 8 divided by 4 is again 2. Pi's will cancel. r in the numerator cancels with one of the r's in the denominator, and so I get 2 dr divided by r is less than or equal to 0.01. Okay, and now what am I trying to find here? I want to know what is the percentage error of the radius. Well, how do we calculate percent error? If we go back up, percent error is the differential over the initial value, right? Now, I have this written here for f, meaning the output of the function, right? But this is actually the same calculation for any variable that you're dealing with. So if I have this inequality here, what I'm trying to isolate for is dr over r, right? That is the differential of the radius over the radius. That's the part I want to get by itself. So how am I going to do that? Well, I can divide both sides by 2. And so I get that dr over r is less than or equal to 0.005 after I divide both sides by 2. And now this is what the relative change can be no greater than, right? The relative change of the radius has to be less than 0.0 or equal to 0.005. And so the last thing I'm going to do is convert this into a percent. So I know that the radius has to be within 0.5% in order for the surface area to be within 1% of its true value. Okay, about how accurately should we measure the radius, right? We can have an error no greater than 0.5%, okay? Or another way of writing this answer is you can say within, 0.5%. Okay, if we calculate the radius of the sphere by anything greater than 0.5% error, right, the surface area is going to have an error that's greater than 1% of its true value. Okay. Okay, now the last thing I want to show you is this exact same question. Yay, more math, right? Not quite. What I want to do though is I want to change this up slightly. Okay, what if same scenario, but what if instead I had asked you about how accurately should we measure the diameter of a sphere so that the surface area is within 1% of its true value? Now, a lot of people instinctively think, okay, if I know the radius has to be within 0.5%, right, and I want to know what the diameter is, I should probably double it, right? So if I double it, that would mean the diameter would have to be within 1%, right? Let's see what happens. Okay, let's do this. So I'm going to go to a blank page here. And what if I had asked for the percent error for the diameter? So that, again, still same goal. Surface area has to be within 1%. Okay. Now, one thing that is going to strike you right away is we don't have a surface area formula in terms of the diameter of the sphere, right? We have a surface area formula in terms of the radius of a sphere, 4 pi r squared, right? But we can do a little bit of substitution here, right? Because what is a radius? A radius is half of a diameter, okay? Now, real quick, I like to use the capital D for diameter just to kind of make it a little bit different from the other D's when we're doing derivatives, okay? But what I can do now is I can take this value for r, half the diameter, and I can plug it into my surface area of a sphere formula. So I'm going to write the surface area in terms of d. This is a very sad formula here, right? You guys are especially sad because you thought the notes were over. But I'm going to go to 4 pi r squared now, and I'm going to go 4 pi, and I'm going to replace the r with a half diameter that's going to be squared. So the surface area as a function of its diameter, 1/2 squared is 1/4 times 4, that goes away, and so we get just pi times the diameter squared. So here's the sad formula. Surface area in terms of diameter. Now, this is not a formula you probably learned back in geometry, right? But we can calculate something like this with just a little substitution, okay? And now what I'm going to do is I'm going to take the derivative of this equation with respect to its input variable, which is diameter. So d over dd. Sorry about all of these d's, okay? Okay, but I can still take a derivative just like any other derivative. So on the left-hand side, I'm going to get the differential of the surface area, right? Oops, I'm sorry, I'm not there yet. I'm going to get the differential for the surface area over the differential of my input variable, d. And on the right-hand side, just power rule. So I get 2 pi times d. And then isolate the differential of the surface area. And so I get 2 pi d times the differential of the diameter dd. Okay, this is one I don't recommend you memorize. All right, but we can use this for now. Okay, so differential of the surface area, right? Now that I know what that is, I can calculate that, again, we're told we want the surface area to be within 1%. So that means differential of the surface area over the surface area with some original diameter has to be less than or equal to 0.01. Now plug in all my formulas. 2 pi times diameter times the differential of the diameter over pi times diameter squared has to be less than or equal to 0.01. And now start canceling things out. Pi's go away. D cancels, leaves me with a d in the denominator. And so now I get 2 times the differential of the diameter over 1 diameter, which is less than or equal to 0.01. I want to know how accurately I should measure the diameter, so I want its percent error. So I'm going to get dd over d, right? I want the differential of the diameter over the diameter by itself. And so you get dd, differential of the diameter over diameter, is less than or equal to 0.005 after we divide both sides by 2. And interestingly enough, what this means is that the percent error for the diameter is actually the same as the radius. Okay. Whew. So we do all of this just to say a very important thing. Anytime a question asks you for the percent error of either the radius or the diameter, you don't have to necessarily flip the formula, right? I took this surface area formula that we know and love, right, is a function of its radius, and I did it in terms of its diameter, right? But I didn't need to because I ended up with the same result. The percentage error for anything involving the radius is actually going to be the same for its diameter. Okay. All right. Because, most people would think, oh, maybe you double it, maybe you half it. Okay. Not quite the case. All right. As a matter of fact, they're going to always have the percent error. How accurately you should measure the radius of an object is how accurately you should measure its diameter as well. Okay. All right. So, one more time, any question that asks you to estimate or figure out how accurately you should measure the diameter, you can measure or you can calculate it for the radius. Any question that says for the radius, you could calculate it with the diameter. So for example, right, if we go back to example 9, right, we could have done all of this in terms of diameter and we would have gotten all of the same answers. Okay. Right? Even though the diameter of the circle is going from 24 to 26, change in the diameter would have been 2 inches. That would not have affected any of my answers. Okay? All right, so we're going to call it a day there. I will see you next time.